Hello, welcome back. In part 2 of the PAME tutorial, we're going to pick up from part 1 where we made an anti-reflective coating. If you recall, we used a 112 nanometer thick layer of homogeneous material of 1.22 index of refraction, and we saw that the reflectance had a minimum around 550 nanometers. Now what I'd like to do is, in the same system, replace this homogeneous material with a nanoparticle film. A nanoparticle film looks something like this. In principle, it's one particle thick, all the particles are equal size, and they're dispersed evenly across a layer. In reality, that's not the case. You see there's clustering, there's gaps, and we'll get back to this in a little while. The reflectance from a bulk film versus a nanoparticle film is much different, and the optical properties of the ensemble is much different than from an individual scatterer. The best resource I've found on the optical properties of nanoparticle films is this book from Michael Quinton. I recommend it highly, and I'll come back to it in part 3 when we talk about nanoparticles with shells in detail. To begin, let's replace this layer with a nanomaterial. PAME has two nanomaterials by default. Both are nanospheres. The difference is that you can choose a nanosphere with shell or a bare nanosphere. A nanosphere with shell reduces to the bare nanosphere in the limit that the shell goes to 0. And this interface is a little more polished, so let's just use this one. Now, the first thing you're going to notice is that this material plot becomes much more interesting, and that's because the nanomaterials have a lot more interesting, so they're a lot more complex materials, so they have more that you can inspect. So let's come to the material, and let's set the diameter of the particles to be 10 nanometers. And let's set the shell thickness to 0. 0 shell means that this is now basically a bare nanoparticle. If the core diameter is 10 nanometers, then in the stack, the interface thickness should be 10 nanometers as well. Otherwise, it doesn't really make much sense to have a 100 nanometer thin film out of 10 nanometer particles. In any case, you see that there's a lot more tabs for the nanomaterial. We have the core material, the shell material, which we're not going to look at, and the medium material. Now, we said that this is a layer of nanoparticles. If light is incident from air and it interacts with the nanoparticles, well, the nanoparticles are also in air. Does that make sense? The nanoparticles are always in some sort of matrix, so we have to set that to air. We can come to medium material, choose medium material. By default, it's water. So we'll just set this to a constant value of 1, which we used before to represent non-dispersive air. And you see that that immediately changes the permittivity of this material. The core material is the gold. So we're using a data set, Johnson and Christie, which is a very common experimental data set for gold. But we can use other values for gold. But before we do that, let's look at the core.permittivity plot. This is the permittivity, or the index of refraction, whichever way you like to think about it, of the gold. And we're interpolating using a linear fit on the Johnson and Christie data. No interpolation would show the actual data points from the experimental data. So if I come to choose core material, let's use a different gold material to show you how this is done. We could pick a model like the Drudy model, but I find that's not very accurate. I'd rather use a database, so we can use the SOPR database or the RI info database. I want to say thanks to the curators that put these together, putting all these free materials out there for us to use. And if we scroll down, all of these files are installed onto your computer when you download PAME and install it. What we want is main AU being gold, and here's the one we're using, Johnson and Christie. Let's use this Lamar Chan. This was released in 2013, and we found that it fits our data very nicely. So I'll select that. And it's just a little different in form, but it gives a nicer fit to the optical properties of the gold. And what we can do is we can look at let's look at the Me theory full cross section. This is the extinction, scattering, and absorption of the 10 nanometer core diameter particles in air. If you had an individual particle sitting in air, it would mostly absorb light. You see the scattering is very small at this dispersion. However, a 50 nanometer particle, now it has a little higher scattering cross section. And a 100 nanometer particle, now the scattering contributes much more. Let's go back to 10. And now we can take a look at the reflectance that this produces. And the reflectance looks a lot like the extinction, it turns out. But what is the density of the film? Recall, we just specified that we have a film. The density is controlled by the surface coverage parameter here, and that's controlled through an effective mixing model. There's several of these in PAME. I like the Maxwell-Garcia model, or the Maxwell-Garnett model with Garcia's modification. Let's try to understand what this is doing. Let's go back to the full permittivity of the layer. If we take the volume fraction of gold to 0, you see that the dielectric function goes back to that for air. In other words, this layer is empty, and so the reflectance behaves as you would expect the reflectance from a air-to-glass interface. Likewise, when we let the fill fraction go up and up and up and actually beyond 100% to pure gold, let's reset this, in that limit, this layer becomes pure gold, and the reflectance through a film of gold, 10 nanometers thick, looks something like this. And all the values in between, these are the effective permittivity of the layer computed by this mixing model at this volume fraction. So let's just say, okay, 25% of the surface is occupied. So that's a film that covers 25% of the available binding sites. What does the reflectance from this look like? Like we saw before, it looks something like the extinction cross-section. We can also look at the absorbance, which is similar, and the transmission. And in the transmission, you have this characteristic dip. So a lot of sensors that are based on nanoparticle films look at the transmission through the film. You see this characteristic shape. If your sensor is based on the reflectance of the film, you see this characteristic peak. And they are related to one another through the absorbance. Okay, let's make it more interesting. What if our core diameter was 25 nanometers? We have to go and change the interface to be 25 nanometers too. Now we can look at the reflectance and we see that did have an effect. And as we make these particles more densely covering the film, now we get a lot of shift in the reflectance. The absorbance, interestingly, always kind of looks like it did in the absorbance is related to the optical extinction. So here's the optical extinction. This always looks like the absorbance, and the transmission has the dip still. So it's interesting the relation between the optical extinction of a single particle and the absorbance in a stack of a nanoparticle film. They seem to be intrinsically related, which may be not an obvious result, because in reality, all of our systems are looking at reflectance or transmission, so we don't even see this relation. What about this K parameter? Well, when you're building layers of nanoparticles, you always have to be aware of what the effective mixing theory is doing. For example, if we want to model a film that has clusters and gaps, we're going to need an effective mixing theory that has been shown to model those accurately. And the K parameter in the Maxwell-Garcia approach is related to the clusters, or the asymmetry of this film. I will be adding more mixing theories to PAME in later versions, so we can get a handle on more and more heterogeneous films. But for now, there's only these 5. If I up the K parameter, you'll see that that has an effect of shifting the reflectance. Let's reset that. We can also come back to the substrate. What about angles? We're only looking at light that's incident at about 0. What if we wanted to look at light that came in at 40 degrees? Well, we can choose our angle range up to 40. Let's increment by 5. Excuse me. Now when I refresh the plot, you see that there is a dispersion in the angles, and you can turn on the legend to see which colors correspond to which angles. For the most part, the angle doesn't have much of an effect, so we could average these if we want to look at the average effect. And when we use fibers later, the fiber affects how these modes are averaged. Okay. Now finally, what if instead of gold I wanted to look at silver for the same exact layer? Well, all I have to do is come to the core material and choose something that is silver. And by putting all these materials and all these parameters together in this interface, PAME makes it really easy to compare materials or systems, or prototyping systems, different materials. Okay, let's go back to silver and use the Johnston and Christie data. Well, let's use the Hagman data. Now when I refresh this, where'd the peak go? Well, I bet it's closer in the 300 region. Yep. So we see that for silver, the resonance peak is shifted much farther to the left in both the permittivity and the reflectance spectrum. Alright, in the next tutorial I'm going to show you how to use nanoparticle layers with protein coatings, and we can start to get into a little more realistic simulations. Thanks.